Okay, as I said, we really need to have a test over the first three chapters. Um, because we're behind on things. We're going to have to keep moving through chapter four. But right now, we're in a fairly easy part of chapter four. We're just limited to do partial derivatives and doing a little bit of some limits, a couple of things that you need to be aware of. Um, Everybody from the homework appears to be in pretty good shape in chapter three. I would recommend, since I've given you problems in pairs and you only do one problem out of a pair, that you run through and make sure you know how to do problem, the other problem in each pair, or the problems in that particular section. Just read them. Say, yeah, I know to do this. I know to do this. Oh, I better work this problem. And if you work the problem and you're not sure of it, get it to me. Okay. Or if it's a big question, I mean, a question that everybody really needs to see an answer to, I'll talk about it in class. Okay. Make sense? I recommend at least that you go back and do the kind of parallel problems. Also, another thing in the homework, where I have a dash between two problems instead of a comma, it means do them all. Okay. Now, it's okay, but there are a couple of those, especially the last one in section 3.3, that's probably a good idea to do all three. It helps you pull a lot of this stuff together. Okay. And I don't think it would take you long to do them, or at least think them through. Think them through. See if you got, look at the problems. Look at the problems in the text. You know how to do them. If you're pretty sure you know how to do them well enough to come in and do them on a test, then you're in good shape. Make sense? Okay. Always glad to answer questions. Um, so I'm going to talk first about section 4.3. Then I'm going to tell you why we're doing 4.1 and 4.2. Okay. 4.3 is kind of the bottom line. It's basically probably going to need more than anything, more than the stuff in 4.1 and 4.2. Doggone it. But that side was blank. Of course, I just erased the problem. I told you I'd rework, but I think I remember what it was. Probably ought to make a note just to be sure it's there when I look for it. Uh, I think that was the function I gave you. If that's not right, if you happen to ask me a question on it, remind me what the function was. Actually, I've got your homework papers here, so I'll know. All right, not your homework, your quiz papers. Okay, so here's a function, two variables. Let's just say it's x squared plus 2y cubed. And let's make it an exponent there. Okay. Now this function has a graph. If I graph has a graph in XYZ space. let's just think, wherever that graph is, f of 1, 1 equals 3. So the shape of this graph in space is mysterious. I could play around with it a little bit. I can't visualize it right off the top of my head. It's not a quadric surface. It's something different. And, you're not always going to be able to visualize a graph. It's just, you know enough about quadric surfaces now, you know there are points in three-dimensional space and there are curves that you get if you slice them and all that stuff, okay? That's what you really need to know to get into partial derivatives of functions of more than one variable. Okay, so f of 1, 1 equals 3, and f of 1.11 equals, let's see, that's going to be 1.21, and that's going to be 2.2. So that should be 3.32, I think. Okay, let's pretend that's right anyway. We'll check it out in a minute and see if it makes sense. All right, well, in 3 dimensions, we got x, y, z. The point 1, 1 is on the line x equals 1. Well, it's in the plane x equals 1. That's actually a plane. But down in the xy plane, confining ourselves with the xy plane, it's on the line x equals 1, y equals 1. And that's a point down here in the xy plane, okay? 0.11. Now, the value is 3. That means there's a z, or x is 1, y is 1, and z is 3. So we come up 3 units here. And this point reflects back to the point 0, 0, 3. I'm sorry, projects to the point on the z-axis. Okay? Does that picture make sense? Visualize that? Okay? Now, f of 1.11, where is the point 1.11? Well, x is now 1.1. Now, I'm going to exaggerate the distance between x equals 1 and x equals 1.1. Because if I just use 1.1, everything's going to be too close together. It's going to be hard to see. So here's the point. Okay, first of all, this point up here is 1, 1, 3. Okay, now, if this is x equals 1.1, then I have to come up here 3.3 units. And this is a little inconvenient. I've already. So I'm going to make this point look a lot higher than it really is. Now, I can connect these points like so. And make this kind of a plane parallel to the xz plane. This second point, of course, is I think it should be 3.31, incidentally. 3.41. Okay, let's get the numbers right. I won't tell you what went on in my brain when I did that. Okay, anyhow, we got this thing here now. This whole quadrilateral that connects these 4 points is in a plane parallel to the XZ plane, isn't it? Because it's above the line y equals 1. Okay. Now, y equals 1 describes a plane parallel to the XZ plane. Okay. Goes all the way above and below y1. All the points in free space where y equals 1 lie directly above or below the line y equals 1 in the XZ plane. I take this picture over here and I'm going to kind of flip it around. So your x direction is here. We'll call that like an x prime axis. So that corresponds to this. That'd be like your x prime axis down here at the base. And then the left altitude of this trapezoid is 3. The right altitude is 3.42. The base, well, x equals 1 here. X equals 1.1 here. Now this x equals 1.1 labels this line, so that's a little confusing. But just focus on this picture. What's the slope of this segment up here? Think about it for a second, then I'll let you say. Okay, the answer I got, this verbal answer, was 1/4.42, and that's, you had the right numbers. It's rise divided by run, so the rise is like 0.42. Now, this isn't to scale, obviously, but rise over run slope is, and I'll write it out, it's 3.41 minus 3 over 0.1. And I said 0.42, 0.41. That 2 keeps sticking in my head. And that's 0.41 over 0.1, which is 4.1. Okay, fair enough. Now, whatever this curve is doing at this point, if I slice, whatever the surface is doing in the vicinity of this point, I can slice the surface by the plane y equals 1. Okay, so here's your surface, here's your x direction, here's your y direction, and here's the plane over here, y equals 1. Here's a surface up here. I slice it here, and I just look at that slice. And it's just a curve, isn't it? If I slice the upper half of a sphere, I take one of these ping pong balls, and if I take a really sharp knife, slice this ping pong ball right there, what do I see? I see circle, right? No matter how I slice the thing, if I slice it with a plane, it's going to give me a circle. Okay, so that circle will correspond to this three-dimensional graph confined to this plane. Or if I do the y equals 1 plane, maybe it'd be here. Okay? That makes sense? So if I slice a sphere, I get a circle. If I slice a sphere with a plane, I get a circle. If I slice a cone with a plane, I get what? An ellipse, a hyperbola, or a parabola, or circle. Of course, the circle's an ellipse. Okay, that's conic sections. Hopefully you have that picture. It's a different subject. We've been over it. Okay, so anyhow, the slope is 4.1. This surface might, it doesn't look like this, but it might look like something like this in the plane. So you can kind of see the slice and you see the curve. Does that make sense? So this is a slice of your three-dimensional surface. It's a one-dimensional curve. And your three-dimensional surface is a two-dimensional object in three-dimensional space. We slice it with a plane and we get a one-dimensional object, which is a curve. Okay. The slope of that curve in the vicinity of x equals 1 is close to 4.1. Okay. Let's find the actual slope. The actual slope at 1, 1, 3 is a partial derivative of f with respect to x. Evaluated for x equals 1, y equals 1. So what we're talking about is the instantaneous slope at this point, or at this point, if we just pull this picture out of the three-dimensional diagram. Now the partial derivative of f with respect to x is calculated very easily. I'm going to ask you to calculate it. Just take the derivative of this thing with respect to x and treat y as a constant. What do you get? Okay. Well, we write the partial derivative with respect to x, not using a d, but using kind of a curly d. That's the partial derivative sign. There's a name for the thing, but I never use the word, so I don't even remember what it is anymore. Okay? It's a partial derivative sign, and that's enough. Okay. Well, what's the derivative with respect to x of x squared? You know, it's 2x. Okay. And then you got 2y cubed x, or if you're using 2xy cubed, it doesn't matter. Well, I say treat y as a constant. So if you got a constant multiple of x, what's the derivative? Well, the derivative of x is just 1. It's just that constant times 1. Okay. Now, why did that work? Well, let's see if it works. Didn't leave myself room to write this, but I'll write it small. At 1, 1. What is the partial of f with respect to x equal? Show me with your fingers. Give you a hint. X is 1 and y is 1. That's what the 1, 1 means, right? So if x is 1 and y is 1, this partial, everybody's waving at me. What is this? It's 4. Yeah, it's 2x plus 2y cubed. Okay. Now this says 4.1. That's close to 4. That's no coincidence. Why is it close to 4? Well, the derivative is the instantaneous slope, the slope of the tangent line, right? This function doesn't have a straight line graph. Between x equals 1 and x equals 1.1, there's some curvature. Okay? It looks like it's kind of an upward curvature because the slope between here and here is greater than the instantaneous slope here. Does that make sense? If it doesn't, ponder it. A little more detail is at this point, the slope is 4. So will be this function is concave up at this point. So let me draw the picture. Again, here's your x prime axis. Here's your point, which is 1, 1, 3. And here's your point, 1, 1, 3.41. Now you see, when I drew this, I drew a straight line from here to here. Well, that straight line doesn't follow the curvature of this thing. Okay? The curvature of this thing is upward. The tangent line at this point in this plane has a slope of 4. Tangent at this point has a slope of 4. That's what the partial derivative told me. The actual secant line between this point and this point had a slope of 0.41 because the function apparently had some upward curvature. Now that picture should make good sense, even though I'm sure I've room to label the secant line up here, but I didn't have that much foresight. And this picture should make sense. This is not really what the function looks like in the plane y equals 1. Well, just a little more. What is the function in the plane y equals 1? If you combine y to be 1, then this function is just x squared plus x. Okay? So this curve here, I really don't have room to label it. It's f of x1 because we confine ourselves to the plane where y equals 1. That's x squared plus x. So that's just your x squared graph, horizontally shifted about a quarter of a unit. And it's concave up here. It's part of a parabola. So what you've got in this plane is actually a parabola. Now it started out looking a little like a parabola, but then I let it do this just because I didn't have room to keep it going up, because I just drew an arbitrary shape, okay? I think we got a question. Okay, and somebody corrected me. Obviously, if y equals 1, we get 2x, not x. So it's x squared plus 2x. Still, it's a parabola. Shift a little bit from x squared, shift a little bit from x squared plus x. But in this vicinity, it's going to have that behavior. If you have that much of a picture, you have a good start on understanding partial derivatives. They're easy to calculate, assuming you have an easy function. And this is an easy function to take a derivative on, okay? Well, that's all great. I'm going to say a little more. Can anybody give me a vector in three-dimensional space whose direction is parallel to the tangent line at that point? So we want a vector the direction in the direction of the line tangent to the surface confined to the one point y equals 1 plane. And let's just say at the point 1, 1, 3. Now there's the point we're talking about, the point represented here, point represented here, point represented here. Doesn't have to be a unit vector, it can be any vector. Any vector in the direction of that tangent line. And of course, if you give me any vector in the direction of the tangent line, we could find a unit vector in the direction of the tangent line, right? Now that's a lot to process, so let me make it a little clearer. Does that vector, and just give me a thumbs up or thumbs down, does that vector have a j component? Yes or no? Well, first of all, that vector would correspond to the vector here. So we just take this tangent line and extend it, there's our vector. Could be any vector in that direction. Okay, now, where does this picture live? It lives in the plane y equals 1, right? So this entire y equals 1 plane is perpendicular to the y-axis, right? Normal vector for the y equals 1 plane is j, unit normal, okay? And this vector is in that plane, meaning it's perpendicular to the normal vector, which means it doesn't have a j component. Jot that down. Okay, I'm going to jot it down over here, just so you have a visual reference to the statement. I can't write that whole statement again. I can, but okay. The desired vector is in the plane y equals 1 whose unit normal vector is j. Could be plus or minus j, but I'll just use j because that's all we really need. Okay. So it has no j component. Okay. Now, does it have an I component? Oh, yeah, the plane's going in the x direction, right? So it has an I component. Are we recording yet? Has an I component. Does it have a k component? Yeah, well, it's in the I direction and it's pointing upward, right? Okay. So what do you think would be a good I component? How long should the I component be? Well, I'm going to suggest that 1 is really a convenient number. Now, any number but 0 would be okay. If 0 wouldn't have an I component, right? But 1 is really convenient. So if the I component is 1, what's the k component? No, thanks. What's the slope? Figures. Wave at me again. Slope is 4. Now, if the I component is 1 and the slope is 4, what's the k component? It's 4. That makes sense? This is a big picture, this real important picture. In a minute, we're going to be able to compute the tangent plane, the equation of the tangent plane, without even seeing the definition of a partial derivative. Then we'll fill in some definitions so you can use them rigorously, okay? So the I component is 1, the k component okay? So I plus k, is the desired tangent vector. A. We could use 2 plus 8k, any multiple of I plus 4k. But I plus 4k is particularly simple because we just need our unit vector in the x or y direction and multiply the k vector by the slope, and the vector then has the right slope. You could, at this point, give me the equation of the line through this point, tangent to the curve. Okay? It's just going to be I plus j plus 3k plus t times I plus 4k. In other words, you got your point, you move along parallel to this vector. Okay? Parallel to that vector, you add t times the vector. That's how you do the parametric equation of a line, right? Okay? So you want to kind of think about that because that's what you're going to be testing over next week, the parametric equation. I'm not going to ask you to find the equation of this tangent line here, except maybe it's an optional problem. Okay? But that's where we're headed. Okay, so hopefully you want to think over this, think through it. This picture. If you get this picture, the whole of chapter 4 is going to be much easier for you. You're going to have a picture to go with all the calculations. You're not going to have to memorize as many formulas, and you're going to know what you're doing there. Okay? Now, you can do more with it. Okay? We just looked at a plane parallel to the line y equals 1. What do you think this thing looks like in a plane parallel, or in the plane x equals 1? Okay? We looked at it in the plane y equals 1. We're going to look at it now in the plane x equals 1. And I shouldn't use blue because I use blue for other things. So orange tends to obliterate anything it touches. So here's the x equals 1 line again. Now, what if we came out to the plane okay, here's the plane y equals 1. Here's the plane y equals 1.1. Then on x equals 1, y equals 1.1, we would have this point. This is the point on 1.1. It's not in the y equals 1 plane now, it's out in front of it, tenth of a unit. Okay? What's the value of the function? Well, x is 1, so you got 1 plus whatever 2y cubed is. What's the cube of 1.1? Everybody knows it's 1.31. Okay? No, 1.331, I'm sorry. As a binomial expansion. Something probably ought to know something about, so kind of squirrel that away for future reference. So if we multiply 1.331 by 2, we get 2.662. That's multiplied by x, but x is 1, so it's 2.62. X squared is 1, so it's 3.62. Okay? So now in this plane above here, we go all the way up to 3.62. So that's going to bring us up to, oh, I don't, maybe here. And let's go ahead and do that in orange. Where's my orange chalk? So this point is 1.1, 3.62. Now, from the 113 point, which is kind of our central point, and I'll kind of make that red. In this plane, I come up here. Now this plane is parallel to the y-axis. X equals constant. It's parallel to the YZ plane, YZ coordinate plane. Okay, so it's like we've got this side here, a side here, and a side here. These two are perpendicular. You got a right angle between here and here. So there's a right angle between this plane and this plane. What's the slope of this line? Okay, so again, what I've done is sketched the intersection of this x equals 1 plane with the surface. Now the surface, if x equals 1, is 1 plus 2y cubed. Just a y cubed graph, just, like an x squared graph, but a little more extreme, okay? And it's 2x cubed, so it's got twice the slope and all that. But between this point where x and y are 1, well, the point where y equals 1 here, and the point where y equals 1.1, the z value goes from 3, which is the z value at this point, to 3.62, which is a value at this point. So we can see that the slope is going to be rise divided by run. From here to here, in this plane, the run goes this way. The run is 0.1, because we went to 0.1, right? The rise is 0.62, if I did my calculation correctly, okay? And, I didn't. I should have another 6 in there. Yeah. Six, 2. Anyhow, that does make a lot of difference, but you get the idea. Okay. So the slope, place to write it. I'll just say the slope in the x equals 1 plane is 6.62, rise 0.662, run 0.1. Now, find the partial derivative of this thing with respect to y. Oh, phooey. I've been known to say bad words when Zoom isn't recording when I want it to be recording, because the dang thing does not show me whether it's recording or not. It does just for a little bit and then it goes away. Maybe I don't know how to operate it. Okay, I'm a little irritated, but that's okay. I love this, so I don't mind going over it again. I think we stopped recording somewhere around the point where I had this picture. Again, this picture, just to briefly summarize, slices the surface it's the graph of this function along the plane z equals 1, x equals 1. Okay, that plane is like in the plane of the board, a little bit in front of the xy plane, 1 unit out from the xy plane. In that plane, see if I wrote it. Well, in that plane, we're going to have the point 1, 1.1 down within the xy plane. It's 1, 1.10 if you do it in 3 dimensions, but right now the important numbers are 1 and 1.1. Okay. Now, when x is 1 and y is 1.1, what's the value of this function? Well, it's 3.662. I think I said 3.62 and then realized there's, the cube of 1.1 is 1.331, and I was leaving off one of the threes when I doubled it. But anyhow, there it is. Okay. Now the picture then depicts this line segment, vertical line segment of length 3.662 coming out of the xy point x 1.1, the xy point 1, 1.1. And there's the point that's on the surface formed by this graph. Now, if I confine this graph to the x equals 1 plane, that means x equals 1, so we got 1 plus 2y cubed. That's an easy graph. That's just a y cubed graph, which is a little more extreme than, and I'm pretty sure that I was recording when I said all that. So we get a curve that kind of looks like this through this point and this point in 3-dimensional space. And now we sketch that curve over here. And let's make sure that's all visible. I think maybe we're missing just a little bit. Okay. Now I've just taken this trapezoid here. Orange trapezoid is kind of emphasized here. And I've redrawn it here. The height on this side is 3. The height on this side is 3.662. So there it is. The width is 1 because here this point is 1, 1. This point is 1, 1.1. Y has increased by 0.1. So we have a trapezoid of the dimensions that we see here. So what's the slope? Okay, somebody gave me a 0.62. And that was when I had 3.62 instead of 3.662. It's actually 6.62. And I didn't write down what the slope was. The rise over run equals 3.662 minus 3. Rise from here to here, 3.662 over the run, which is 0.1, which is 6.62. And I did write that, but I wrote it over here. Okay. I started right it here. Now let's compare partial to f with respect to y is what? Treat x as a constant. X squared is constant, it's got a 0 derivative. Y cubed has a derivative of 3y squared. 2 times that is 6y squared times x. So there's your partial of f with respect to y. That's at any point. At the point where x and y are both equal to 1, which is this point here on the graph, we get the partial of f with respect to y is 6. And plug in 1 for x and 1 for y, it's obvious we get 6. Now my question is, what's a tangent line? Okay, well, I've drawn a tangent line. I've drawn a white curve here, and I've drawn a tangent line. Just as we did before, we can say, well, the direction from here to here, we go back to the picture, is the y direction, so that j is a vector in this direction. if we use 1 as the j component, so this is j plus something, it's got to be j plus the slope times k, just as it was over here, I plus the slope times k. So we get a tangent line and a tangent vector. Labeled just a little incomplete. There's the tangent line. The tangent vector is j plus 6k. So what can we do with this? Make a couple of statements. The vector I plus 4k is tangent to this surface, and it's in the x direction, sort of, in the x plane parallel to the xz plane. And j plus 6k is a vector that's tangent to the surface in the plane parallel to the yz plane. These are both parallel then to lines that are tangent to the graph of this function at the point 113. We can therefore take the cross product and get a vector that's normal to the plane tangent to the function at this point. Now we're going to have a vector normal to the plane and a point on the plane, so it's really easy to write the equation for the plane. And you did that by habit a couple of weeks ago. You want to incorporate it so where you really understand the geometry and everything, so you don't have to rely on an equation you might memorize incorrectly. But you also want to memorize that equation so you can compare that with your geometric intuition. Well, anyhow, you find the equation of the tangent plane and use that, then what's good is it you can use it to approximate the values of f of x, y near x equals 1 and y equals 1. Okay. And that's really kind of easy to do. So, we've got some stuff here about lines and planes. You should probably, just as an exercise, find the equation of the line here. Find the equation of the line that we got in the xz plane, or parallel to the xz plane. And find the equation of this plane here. And maybe even verify that gives you a good approximation to the value of the function, let's say, at the point xy point 1.03, 1.07, or 0.96, 1.3, whatever. Okay. Plug those coordinates into the tangent plane, plug those coordinates into the function, you're going to get values that are pretty similar. Now, the further you get from the point 1.1, the more the actual surface curves away from the tangent plane, and the less accurate the approximation of the tangent plane is going to be. And as I said to everybody, you want to try to digest this whole picture, because if you got this picture, it pretty much makes everything else in the rest of this course and in preceding parts of this course a little clearer, a whole lot clearer. Okay, so do what's necessary, get this picture in your mind, and you're going to be happy that you have it. Okay. Okay. Anyhow, see you in a couple of days. There'll be a homework assignment. It'll be posted. And I'll also say the homework is going to change a little bit from what I posted earlier.